John here. So I'm all excited. I finished my sign. The timer is timing and the counter is counting and the display is updating and everything's really exciting except for one problem. Like I said in the last video, there's a problem. What is the problem? Well, if you look closely, this will fall behind by about 4 seconds every minute. That's not very good as a timer. I mean, we're talking about an 8% error. That's huge. I don't really want to be affiliated with something of such substandard quality as an 8% error on a clock. That's just terrible. So let's look into the details as to why this is and how to fix it. Okay, so let's go find our Arduino code. Here's the program, okay? Here's a program from Timer 3 that I put on a GitHub that does work, but like I said, it runs a little slow. What is this really doing? I'm asking what time it is each time through this loop, and I say if it's time to update my sign, I'll update my sign. Every time I update the sign, I say the next time to update the sign is 100 milliseconds into the future of the last time that I was supposed to update the sign. And this would work fine, provided that this function here gives me the correct time. In reality, it does not. Why does it not do that? Well, this thing, the way it's implemented in the Arduino software, is 1,000 times a second. An interrupt is generated that tells the CPU and the Arduino to stop doing whatever it's doing, go off somewhere and add 1 to the millisecond timer count value, and then return and resume to what it was doing. And as long as that works, this would be fine. And it would, except for one problem. This function right here in the Adafruit Library, if you read the Adafruit Library documentation, you'd know that when you go into this routine, what that routine does is it shuts off the interrupts. It then downloads the data into the LEDs, and then it turns the interrupts back on. Now, it has to do this for technical reasons. It has to do with timing and things like that. Very specific timing needs of the LEDs. All right, so it turns out that I'll show you in a second. Well, because I have like 296 LEDs in my sign, it takes a little while to send the data over to the LEDs. That's the short of it right there. By the time it gets back over here to come around the loop again, so much time has passed that a lot of interrupts have been missed. And by the time I ask what milliseconds have, the new millisecond time, it'll have been delayed. So it loses time every time I update the display. Now, how much time was that really? I mean, you know, why should it take so long? Well, if you look at the data sheet for the LEDs that come on the strips that I purchased. If you open up the box and the packaging and you look, you can see it says on the label that I have WS2812B LEDs on the strip. So here's the data sheet for that strip. First of all, it says you can send data to the strip at 800 kbits a second. All right, well, quick little fun fact. Remember up here, the magical macros up here when we created our pixel strip a few videos ago? Hiding in there is this 800 kilohertz. Now you know why. We need to tell the Adafruit Library with the speed that the LEDs run at, and that comes from the data sheet right here. Well, while we're looking around, this over here where it says GRB comes from somewhere else in the data sheet. This is why you need to read the data sheet if you actually want to write any low-level library code. It's because the data sheet, among other things, tells you to send the green data before the red and the blue data when you send the color information in GRB order. All right, so little side fun fact there, demystifying some of these macros. Okay, so what's the problem here? All right, so here's the problem. The 800 kilohertz bit rate is derived from the fact that they give you these timing numbers here. If you want to send a binary 1 bit to the LED, do this. If you want to send a binary 0 bit, do that, and use these specific time values. The short of it is, the length of these signals here are defined in the table we were just looking at. The OH and the OL values, you look them all up in here, and you find out that is in fact 800 kilohertz is the speed you need to send the data. And because of this chart down here, it says every time you send the data for one single LED, you need to send 24 bits of data. So if you do the math, you get what? Hopefully this will come out right. If you say I have 296 LEDs, and each one of them has 24 bits, that's a total of 7,104 bits divided by 800 kilohertz. It takes that long to update my sign. Well, this is just over 8 milliseconds, which means I'm probably going to lose 8 interrupts while I'm updating the display, so that the next time I call this millis function up here in my code, I will have lost several ticks on the clock. Well, what's about 8%? Well, in 1 minute, there's 60 seconds. And if I multiply that by 0.08 to say what's 8% of 60 seconds, it's about 4 seconds. So we've now just figured out where the 4 seconds are going, why I fall behind. There's just overwhelming evidence to support the fact that, the theory that using the Adafruit library is causing me to lose time on my millisecond timer. So how do we fix this? Well, we have a couple of options. We can redesign the Adafruit library, or we can change the way the timer works. Notice the code runs through, well, first of all, I don't want to rewrite the Adafruit code. I opened it up and looked at it. It's fairly complicated because it has a lot of code in there to get the timing just right to talk to the LEDs. So you then can open up and look at the timer code, much simpler. So if we're going to hack up something, let's hack up the timer code. The timer code makes a lot of sense anyway, because if you look here, what we're really doing in this loop is we're saying, look, out of every time the millisecond timer is updated, I only care 1 out of 100 times. The clock is running 100 times faster than we need it to go. So why bother? If I simply ran the clock at the speed that I wanted, it would go very slowly at 10 hertz instead of 100, or rather, instead of 1,000 hertz. If I only ran it at 10 hertz, what would happen is I would generate my interrupt to update my clock. I would then notice the clock had changed, update my period, download my stuff, flush the data out to the strip, and this would complete in the 8 or 9 milliseconds. Well, my interrupt handler, my clock, would not go off for another 100 milliseconds. So I had plenty of time to do all this work and get back up here and check my clock again without ever missing any interrupts. So this will keep perfect time if we can figure out how to do that. So let's go figure out how to do that. Blah, 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 blah. I got timer number 5. Okay, so let's throw away number 3. And look at code version number 5. Now all I've done in here, the only differences between these two versions of the code is that I've changed my timing. As you see, I commented some stuff out and I changed my period to 1 and so on. And up here, I created my own clock handler. That's it. This is the entire source code of what you do to set up your own clock. So let's look at the changes. Starting at the top, I added my this call to init timer in my setup routine, which does this one time during the startup of my application. So what does this do? I shut off interrupts. I play some games with some magical registers, and then I re-enable the interrupts. Now there's several websites that talk about how timers work on the Arduino. The definitive source, if you really want to know, you have to open up the AVR manual and read the doc for this specific chip that's on the Arduino, which is an ATmega 328PU. And there is a manual online for it, and it'll tell you all of the details of the timers. It may be a little bit technical and hard to read. Sometimes you need to read that along with some Google searches and whatnot to kind of figure out what's going on if you're new to datasheets. But the short of it is, you can initialize a couple of values in the Arduino processor, in the ATmega processor, to tell it to create a timer that runs at the speed that you want. And every time the timer times out, call some function whose name is kind of a magical thing that's based on the software library. And in that function, you just do what you want to do. I'm going to add 1 to my clock, and this is going to happen 10 times a second. The quick run through here is these settings here and these settings here tell the timer to run in a specific mode. There's different modes they can run in, PWMs to work servos and other things to measure time in different ways. The time I'm using is called counter timer mode or counter timer compare mode, or it depends on the chip. I can never remember which brands use what words. But the counting and timing mode, what it does is it counts up to a number. In this case, it's that number right there. And then it resets itself back to 0 and counts up to that number again, resets itself back to 0, and just does this forever. Every time it resets itself back to 0, it generates an interrupt and calls this function and does that. It's as simple as that. If you Google search for this kind of a message on the internet, you see no shortage of websites that talk about this, and you see this exact same code in slight variations on every one of those sites if you really want to know all the details. The short of it is, we know that the Arduino runs at 16 megahertz for its master clock. I'm going to tell the Arduino chip to divide that by 256 and then take the result of that and divide that by 6,249, and that turns out to be one less than the correct number to give myself 10 hertz. This extra -1 that I took off of here is because if you read the Arduino spec, it says that number has to be one less than the number you really want, because it takes one extra clock cycle to generate that interrupt, so to speak. So this is all you have to do to create your own timer. You can run it at whatever speed you want within reason. This number can only be so big and so on, but you can go ahead and read the doc and find out all about that. So what do I got? I got a global variable somewhere that just counts up over time. That global variable is right here. This might be a little bit new to you. It's called volatile. Whenever you have a variable that's modified by two different places potentially at the same time, like an interrupt handler that wants to add 1 to a value that might be read in your code. Remember, an interrupt tells the CPU to stop doing what it's doing, go off, do something else, and then resume what it's doing. Well, you need to make sure that the compiler makes sure to always read the value of this variable. You can Google search on what it means to create volatile variables in C and C++, learn all about that. Short of it is, if you got variables in an interrupt handler that you also want to read in your regular old code, make it volatile. Okay. Now, let's go back to what we did over here. I'm not going to call millis. I'm just going to go grab the value from my clock. I don't need to use millis anymore. We also have to disable interrupts and re-enable interrupts while I steal a copy of the value from my clock counter. The reason that's true is because the AVR is kind of old, a couple of decades old style technology. It has 8-bit registers, and my clock is a 32-bit value, which means it has to fetch 4 bytes out of memory in order to get the value into my other variable over here. That takes multiple instructions, that takes time. If the clock should go off by coincidence while I'm making my copy of this variable, I'm going to have a problem. I'll get a garbage number and it'll screw up my code and it won't count at the right rate. So what I need to do is shut off interrupts just for a brief moment so that I can steal that copy, turn them back on, and then go back to business as usual. So what else is going on in here? Instead of waiting 100 milliseconds for my time period, I'm going to wait 1 because now I'm in tenths. I should change my documentation and call this tenths per tick. All right. Now that's good. I got my own clock, and the rest of the code is the same as it ever was before. Now I can't miss interrupts because they don't happen as often, and this still takes the same amount of time, which is on the order of 8 or 9 milliseconds. This thing over here changes only once every 100 milliseconds, so I can't have that problem anymore. And now my clock will run at the right speed. Let's download this, make sure it works. Would be nice. Always when demonstrating something. Hey, okay. So I'll push this up to GitHub. We're done. Thank you very much for watching. If you found this useful, feel free to drop me a comment, give me a thumbs up. If you think it's terrible, I don't know, send me another comment, thumbs down. Let me know. Thanks. I'll see you later.